Derivatives only take us so far in calculus. In order to really get some good applications and use out of this discipline, we need the inverse of the derivative, or the antiderivative, or what we call the integral. So that was the last part of your previous course. What we're going to do is run through a quick review of this. The rest of the course, not that we'll stop taking derivatives, but we'll be using integration nonstop, so you'll get back into a groove pretty quick. The good thing about integration is there really are, for this course, are only three rules for us. We kind of have this power rule, the antiderivative of two specific functions. Don't forget, with the natural log, we have the absolute value around x. And then we have our constant multiple rule and our sum rule. The bad news is that means everything else for integration is going to be method. We're going to have to turn things into these formulas here. And you've seen substitution method. You've probably seen integration by parts. Certainly algebraic approaches are going to be important as well. So this box here is just a summary of what you saw in your last course. And then, of course, for definite integrals, we have our fundamental theorem of calculus. And whenever you see the name of a subject preceded by fundamental theorem of, it's a big deal. You've only seen a couple fundamental theorems in mathematics. One was for arithmetic, one was for algebra. Both of them were just about factoring numbers or polynomials. This is a big deal. This connects the two halves of calculus, the differential with the integral half. So probably an in-between step here, just to remind you of the notation. You would find the antiderivative f at x, and then remember, we switch after you've antidifferentiated, we switch to this vertical bar notation, and it just means evaluate. Basically, this means that. Okay, it's just we need some in-between step because you can't do the antiderivative and plug all the numbers in at the same time. It's just too much. So let's get back into this and bring back some of our integration methods by running through a bunch of examples. So this first one here, all three of these functions are power functions, but just like differentiation, we want to get rid of the radical or the negative, bring in negative exponents to get rid of the fraction. Most of the time, any prep that you would have done for taking a derivative is the same prep you would do for an antiderivative. So the first term's fine, but we can bring the denominator up using negative exponents. We can get rid of that radical by writing this as x to the 3/2 dx. And now we just use the sum rule, constant multiple rule, and power rule in reverse and integrate term by term. So remember, when we differentiate, we reduce the exponent by 1. So if we integrate, we're going to add 1 to the exponent and then multiply by the reciprocal. And the good thing about integration is you can take the derivative on the fly to check your answers. So if I took the derivative of this, 4 times 1/4 is 1, x to the 4 minus 1 is x cubed. And so if we continue on here, we'd have negative 3 times, I started taking the derivative. We're going to have minus, we're going to add 1 to the exponent, so this would become negative 2, and we're going to multiply by the reciprocal of our new exponent. And then we have plus. Over here, we're going to add 1, so that would give me 5/2, and then we're going to multiply by the reciprocal. So what's wrong at this point? Well, this is only one function whose derivative is the function we started with. We want all of them. So don't forget your constant. Okay? And then we can just clean up the fraction business. So this is 1/4 x to the 4th plus 1/2 x to the negative 2 plus 2/5 x to the 5/2 plus c. And you can leave it like this. There's no reason to go back to the root notation or to bring this back down to the bottom. Of course, you could write this term as 1 over 2x squared, but I don't think that's just an extra step for cosmetic purposes. So I don't think you need to do that. Likewise here, this would be, try that again, the square root of x to the fifth. So it might show up in the back of the book that way, but I don't think for our purposes there's any real need to do this. At least not until you have a reason, if you're going to do algebra or something like that. But if you're just going to plug numbers in, you got a calculator to do the work, so I wouldn't bother with that. So don't forget that we're getting infinitely many functions whose derivative is the original, because the derivative of a constant is 0. So let's look at a definite integral. So in part B here, when we take the antiderivative, so this is kind of this in-between step I referenced up above, we're going to find the general antiderivative, 1/3 x to the third plus 5 halves x squared minus 4x plus c. And then we evaluate it from 1 to 2. So make sure you change the notation. After you've done the antiderivative, the integral symbol should be gone, and you just have this evaluation bar. And so what happens here, we have 1/3, 2 cubed plus 5 halves, 2 squared. So the first term we evaluate at the upper limit, which is 2. Then we have plus c, minus, and then we evaluate at the lower limit. Oh, that's a 3. So we have 5 halves times 1 squared minus 4 times 1 plus c. So what happens to the constant? Well, that negative sign's going to be distributed through this parenthetical expression, and so we'll have c minus c. So this is why we don't include the constant with definite integrals, is it would always subtract away. And then if you clean up with what's left here, I got 35 over 6. Okay, so the big difference here is that for indefinite integrals, so this is definite and this is indefinite. So indefinite integrals, you get infinitely many functions, a family of functions. And with definite integrals, you get a numerical answer. Okay. Other than that, the process is almost the same. You just have, for a definite integral, the last step of plugging the numbers in, but you still do the antiderivative part. So let's scroll down here and look at part C. Okay, so for this, on the first step, you're not really worried about the -1 or the 1. It is a definite integral, but you still have to find the antiderivative. So be careful with exponentials that you're not taking the derivative. This will be 1/5 e to the 5x. I'm going to leave off the plus c. We now remember that the c's drop out, and this gets evaluated from -1 to 1. And so this will be 1/5 e to the 5 times 1 minus e to the 5 times -1. You could include the 1/5 on each term, but I think it's easier just to leave it out in front. And so we end up with 1/5 times e to the 5th minus e to the -5. And I would just leave it right there. That's a 5. If this were an application problem or something, then definitely you would go to decimal, so that would make some sense. Okay, so that's it for the easier problems. Now we want to move on to some methods. So on the next page, we'll review substitution. That's really your biggest method, but integration by parts will be important for us as well. So let's move on to page 7.